So I don't think any discussion of reactions and reaction rates would really be complete without a discussion of intermediate reactions. So we're going to be talking a little bit about those now. Okay, so let's just start with like a really basic chemical equation, right? So 2NO plus O2 gives me 2NO2, right? So this is a pretty like standard balanced chemical equation, right? We're familiar with these, where here we have our reactants, and here we have our products. Except in the real world, it's not really that simple. In the same way that, when you cook, you're not necessarily just taking all of your ingredients and dumping them in a pot and then magically a meal comes out, right? It's not necessarily really the case in real life that you simply throw some reactants together and magically these products are created, right? Instead, very often what we get are intermediate reactions. So essentially these guys have to go through a little bit of rigmarole, the reactants do, before we can reach our final product. And in this case, this is actually ends up being a two-step process, right? So we're starting off with our 2 mole of nitrous oxide and some diatomic oxygen, right? And what happens is we get some N2O2. Then that N2O2 combines with the remaining oxygen, and that, in fact, is what gives us our NO2, like that, right? So there's an extra wrinkle here, which is that this part of the process happens pretty quickly, right? This is a pretty fast reaction. On the other hand, this guy's a pretty slow reaction. Any thoughts on why maybe this guy would be a little bit slower than this guy up here? Think back to our original conversation about the factors that can affect reaction rate. And you might recall that we talked a little bit about concentration. We've already used up some of this diatomic oxygen, right? We used it up creating this guy, right? So now this guy's got to interact with more oxygen, except we don't have as much to work with as we did before, potentially, right? So that could be slowing down the reaction. Also, keep in mind, we only have so much of this to work with at any given point in time, so that's potentially limiting the reaction. The main thing to keep in mind here is that the overall reaction rate for this guy, for this final product, is going to be limited by this rate, right? No matter how fast this guy is, it doesn't make a difference if this guy is super slow, right? One of the metaphors that I believe it's the Princeton Review Study Guide uses is this idea of, washing dishes and drying dishes, right? Doesn't matter how fast your dishwasher is, right? If the guy drying is super slow, you're not necessarily going to get done any faster. So hopefully that makes sense. Okay, so the thing we just described, essentially the number of steps, however many it is, that's required to complete a reaction is what sometimes is referred to as the reaction mechanism, right? The series of steps by which the reacting particles rearrange themselves to get from reactants to products is the reaction mechanism, right? So I just wanted to take a look at a sample problem, right? Again, this is Bogarted from Princeton Review. What up, Princeton Review? We love you. So let's just talk a smidge here about this problem, what we're seeing. Which of the following is true about the hypothetical two-step reaction shown below? So again, they're just giving you kind of like a hypothetical two-step. In the first step, we've got substance A plus substance 2B gives us substance C plus 2D, right? And then C gives you A plus E, right? So then the final product, if we were going to write this out as like one big kind of collated equation, it would just be when you take A and add to B, right? You end up with A plus E, right? Reactants, products. Make sense? Okay, so they're asking you what's true. Notice the pattern we're seeing here. They're telling you one of these things is a catalyst, either A or B is a catalyst, and one of these things is an intermediate, either C, D, or A is an intermediate. Okay, so what does the word intermediate mean? Well, in this case, it pretty much just means, again, that it's something that only shows up in the sort of in-between or intermediate reaction. So up here in our original example, for instance, N2O2 was our intermediate because it showed up here, but as you can see if you look above, it is nowhere in our finished equation, right? It's nowhere in the finished equation. So that's, if that helps you to sort of visualize. Let's see, let's do a new color. I'm feeling kind of orangey at the moment. I'm not sure why, I just am. Okay, so first question is, what's my intermediate here, right? Essentially, what stuff is showing up in the first equation and in the second equation, but not in the finished equation? That's right. You guessed it. C is the thing that's showing up in the first equation and in the second equation, but nowhere in the finished equation. So C is my intermediate. That allows me to do a little process elimination. It can't be B, it can't be C, it's got to be either A or D. Okay, so now the question is, which one of these two things is my catalyst? Okay, well, let's recall what a catalyst is. This is something you learned about in previous videos. Remember, a catalyst ultimately is just a substance that sort of shows up in order to speed up your reaction, right? A substance that speeds the reaction. But, and here's the important bit, is not itself reacted. So the question then becomes, in the final equation, is there anything that shows up kind of at both ends but doesn't appear to have anything really done to it all? And if you look, you'll see, oh yeah, that's clearly A. A shows up at the beginning, gets spat out at the end, but nothing really happens to it in between, right? So that means A is my catalyst, and A is my answer. Great, and now I think you guys probably know pretty much everything you're going to need for the SAT about rates of reaction and the rate law.